Last video, I left you with a puzzle.
Now this is
The
interesting.
setup involves two sliding blocks in a perfectly
puzzle.
idealized world where there's no friction and all collisions are perfectly elastic, meaning no energy is lost. One block is sent towards another smaller one, which starts off stationary, and there's a wall behind it, so that the smaller block bounces back and forth until it redirects the big block's momentum enough to fully turn around, sailing away from the wall. If that first block has a mass which is a power of 100 times the mass of the second, for example, 1,000,000 times as much, an insanely surprising fact popped out. The total number of collisions, including those between the second mass and the wall,
I want to see how fast that
including those
accelerated.
between the second mass and the wall of the second, for example, 1,000,000 times as much, an insanely surprising fact popped out. The total number of collisions,
Oh, you can't
including
see
those
shit.
between the second mass and the wall, has the same starting digits as pi. In this example, that's 3,141 collisions. If that first block was 1,000,000,000 times the mass, it would be 3,141,592 collisions before this happens, almost all of which happen in one huge, unrealistic burst. And speaking of unexpectedly big bursts, in the short time since that video went out, lots of people have been sharing solutions and attempts and simulations, which is awesome. So why does this happen? Why should pi show up in such an unexpected place and in such an unexpected manner? Foremost, this is a lesson about using phase space, also commonly called configuration space, to solve problems. So rest assured that you're not just learning about some esoteric algorithm for pi. This tactic here is core to many other fields, and it's a useful tool to keep in your belt. To start, when one block hits another, how do you figure out the velocity of each one after the collision? The key is to use the conservation of energy together with the conservation of momentum.
Of course.
Let's go ahead and call their masses m1 and m2, and their velocities v1 and v2, which will be the variables changing throughout the process. At any given point, the total kinetic energy is 1/2 m1 times v1 squared plus 1/2 m2.
I say this sarcastically, but
so even though v1 and v2 will be changing
this
as the blocks get bumped around, the value of this expression must remain constant. The total momentum of the two blocks is m1 times v1 plus m2 times v2. This also has to remain constant when the blocks hit each other, but it can change as the second block bounces off the wall. In reality, the second block would transfer its momentum to the wall during this collision, and again, we're being idealistic, say thinking of that wall as having infinite mass, so such a momentum transfer won't actually move the wall. So here we have two equations and unknowns. To put these to use, try drawing a picture to represent
so the wall is your mom.
Let's start by focusing on the energy equation. Since v1 and v2 are changing, maybe you think to represent the equation on a coordinate plane where x is equal to v1 and y is equal to v2. So individual points on this plane encode the pair of velocities of our block. In that case, the energy equation represents an ellipse, where each point of this ellipse gives you a pair of velocities, all of which correspond to the same total kinetic energy. In fact, let's actually change our coordinates a little bit to make this into a perfect circle, since we know that we're on a hunt for pi. Instead of having the x-coordinate represent v1, let it be the square root of m1 times v1, which for this example shown stretches the figure in the x direction by the square root of 10. Likewise, have the y-coordinate represent square root of m2 times v2. That way, when you look at the conservation of energy equation, what it's saying is 1/2 x squared plus y squared equals some constant, which is the equation for a circle. Which specific circle depends on the total energy, but that actually doesn't matter for our problem. At the beginning, when the first block is sliding to the left and the second one is stationary, we're at the leftmost point on the circle, right? Where the x-coordinate is negative.
This is
and
the Minecraft
y-coordinate
coordinates again.
What
this
about
is the
right
science
after the
we have to
collision?
go through.
How do we know what happens? Conservation of energy tells us that we must jump to some other point of the circle, but which one? Well, use the conservation of momentum. This tells us that before and after the collision, the value of m1 times v1 plus m2 times v2 must stay constant. In our rescaled coordinates, that looks like saying square root of m1 times x plus square root of m2 times y equals some constant. And that's the equation for a line, specifically a line with a slope of negative square root of m1 over m2. You might ask which specific line, and that depends on what the constant momentum is. But we know that it must pass through our first point, and that locks us into one choice. So just to be clear about what all this is saying, all other pairs of velocities which would give the same momentum live on this line, in just the same way that all other pairs of velocities that give the same energy live on this circle. So notice, this gives us one and only one other point.
Alright, we're never gonna use this ever in
and
our
it should
entire
make sense
lives.
that it's something where...
I get it. I kinda get it. But it's fucking useless, dude. It's fucking useless. Ah, is it useless? Yes. XD7K donates says